welcome to True Projects. In this video, we are going to explain about the project, which is ECRNet Hybrid Network for Skin Cancer Identification. Before getting into the execution, first let us understand what is the project about. So, what is the skin cancer? Skin cancer is a type of cancer that begins in the skin cells. And this happens when the cells in the skin start growing abnormally and also uncontrollably, forming a tumor. It is one of the most common types of cancer, mainly because our skin is the largest organ that is constantly exposed to harmful factors like ultraviolet radiation from the sun, that is nothing but UV radiation. So, these are different types of skin cancers, with the most common being basal cell carcinoma, squamous cell carcinoma, and the melanoma. Melanoma is the most dangerous because it can spread to other parts of the body, making it harder to treat. So, the main risk factor for skin cancer is prolonged sun exposure, but the other factors like tanning beds and genetic predisposition can also increase the risk. Skin cancer is visible on the skin, so it is easier to detect it early stages. So, early detection is very important of this skin cancer. This is why early detection is so important. Skin cancer is often visible, so it is easier to detect in early stages, and this is why early detection is so important. It increases the chances of successful treatment and helps preventing from spreading. That's why people are encouraged to regularly check their skin for any unusual changes like new moles, growths, or changes in the appearances of existing ones. In the past, skin cancer used to rely on heavily manually extracting features from images like shape, texture, and color. While these approaches worked to some extent, it had its downsides, mainly because it was prone to subjective bias. Different doctors might interpret the same image in slightly different ways, which made the process more complex and less consistent. So, with the rise in artificial intelligence and also deep learning, things have changed a lot. These technologies have brought major improvements to medical imaging by automating the process and also allowing for more accurate analysis. However, there are still some challenges. Take convolutional neural network, for example. These networks are great at picking up local features in the images like edges or patterns, but they have trouble in understanding the bigger picture. To accurately identify skin cancer, it is not just about looking at small local details, but also understanding how these details relate to the larger context of lesion. Things like overall shape, size, and how it fits with the surrounding skin. This is where current methods still fall short. And it's why that is why we need to find better ways to improve the accuracy and make skin cancer detection more reliable. So, in this system, we are proposing the model called ECRNet. It is designed to improve how we recognize skin cancer by tackling some of the issues with traditional methods like CNNs and transformer models. CNNs are really good at picking up small local features like overall edges, but where they fall short is understanding the bigger picture. We have already told you, right? For instance, they might not capture things like shape, size, or symmetry of the lesion, which are crucial for accurately diagnosing the skin cancer. On the other hand, transformer models are great for understanding long range dependencies and relationships in the data, meaning they can capture the broader context. However, they come with the downside. They are computationally expensive and tend to struggle with extracting the smaller local features. So, they are also important. So, to overcome these challenges in this project, we are proposing ECRNet. So, here we are proposing the ECRNet by using ICIC 2018 dataset to train and evaluate models. So this dataset is well established and contains lot of skin cancer images, which helps us to ensure the system performs well and it can accurately classify the skin cancer. Essentially, we are combining strengths of both the approaches to make skin cancer detection more precise and efficient. Along with ECRNet, the system also incorporates soft attention CNN to improve how we analyze and classify skin diseases. This model adds something called attention mechanisms, which helps the system focus on most important parts of the skin images. Think it of like this: when doctors look at skin lesions, they pay extra attention to certain areas that seem suspicious, like irregular shapes or unusual colors. Similarly, the soft attention CNN does the same. It learns to focus more on the areas of the image that are most likely to contain features related to skin cancer. By giving more attention to these important regions, the model becomes much better at recognizing and classifying the skin disease accurately. This leads to more reliable diagnosis and better performance in detection skincare. So, as an extension of this project, we have considered, that is, we have incorporated exception and NASANet, combining them, making an ensemble model to further improve the performance, that is, to enhance the analysis of skin cancer images. By combining these models, we are leveraging the strengths of each one, which helps to improve the overall accuracy and robustness. This ensemble approach allows the system to make more reliable predictions when classifying skin cancer. And we also have integrated different versions of the YOLO, that is YOLO family, which are commonly used for detecting objects in the images. So we are doing as an extension detection part. In this case, here we are used to spot abnormalities in the skin images like unusual growths or lesions. This addition helps the system quickly and accurately identify potential skin cancer lesions, improving its precision in detection. Moving on to the front end part, we have built front end using Flask framework. So, this interface allows users to test the model and interact with it directly. Additionally, we have included user authentication to ensure secure access, making sure that only authorized individuals can use the system. This setup makes the system not only powerful but also practical. Moving on to implementation of the project, we have followed the steps in the flow of work. As we are going to do detection and classification, we have followed different set of steps for classification as well as detection. So coming to classification, first what we have done is we started importing necessary libraries and packages for data processing and model building. Then we explore the data set. So this step involves loading the data set of skin cancer images. We inspect data to understand its structure, labels, and characteristics before training the model. Then we do basic pre-processing of the images. So images are resized to a consistent size for processing, and a shear transformation is applied to slightly tilt the image, helping model generalize better. And the images are zoomed in or out to simulate various perspectives. And then the images are flipped horizontally to create more variations and prevent overfitting. Coming to reshaping, the images are reshaped to match the input requirements of the model. Then we define Then we set up early stopping, which will stop the training of the models if the model's performance stops improving, avoiding overfitting or underfitting. Then the model architecture is called either from a predefined setup or imported from a saved file. Coming to building the model, here we build the model by adding layers like convolution layers, pooling layers, etc., and then train it on the skin cancer data using defined image and labels. Lastly, after training, we save the model with the best performance for later use in detecting skin abnormalities. This is how we do the classification. These are the steps we have followed for classification purpose. Moving on to detection, similar to classification, we have imported necessary packages for image detection such as OpenCV and YOLO specific libraries. Coming to exploring the dataset. Here we load and read the input image for detection, display the image for visualization before any processing is applied. The next step is image processing. So the image is converted into a blob, that is binary large object, for compatibility with the YOLO model. Coming to defining the classes, that is type of the objects in the image, are defined for the detection like skin cancer lesion. Declaring the bounding box. So here the area of interest where there is a skin lesion, that is skin cancer, is identified using a bounding box. Then image array is converted to a NumPy array for model compatibility. Coming to loading the pre-trained model. So what do? We load the pre-trained YOLO model, which contain layers for detecting different objects. And then we extract the layers that produce the final output indicating detected objects. Coming to image processing. Here, we annotate files and images. Attach annotations like labels and positions to images for training. And then, since YOLO uses BGR format, we convert image to RGB. So here images are converted from BGR to RGB. Coming to creating the mask here, mask is created to focus on the region of interest in the image. Then the images is resized to fit the input of the model. Then we do basic data augmentation. We do random transformations that are applied to the image of for more diverse data. Then images are rotated to simulate different angles, and further transformations like shifting, scaling are applied to increase the variation. And then we install basic packages that are required. Install any necessary dependencies or packages required for processing and running the YOLO model. And then prepare the data in a format that is compatible with the YOLO family models for object detection. And then we define and construct the model architecture using YOLO or similar detection networks. And we train the YOLO model on the dataset, adjusting the weights to optimize object detection performance. And then after training, we save the model that performs the best for detecting abnormalities in the skin images. Moving to the front end part. Front end of the project is built using Flask, a Python web framework that allows us to create a user-friendly platform for interacting with the model. And then using the data, the front end utilizes the trained classification and detection models to process the user uploaded images. And in the front end users, they will be uploading images. So the system classifies the skin lesion as benign or malignant. In this way, users they will be able to upload those images in the front end, and that will be processed at the back end for classification or detection. And the trained model will be giving it will be feeded to the trained model, that is images uploaded in the front end will be feeded with the trained model, and that will be giving the prediction in the front end of the project. Moving on to the algorithms used to implement this project, we have used set of algorithms. So for classifying the skin cancers, we have used all the set of algorithms. This is the proposed model and this is the extension model that we have applied for classification. Moving on to the detection part, we have implemented these algorithms. We have implemented different versions of the YOLO for detecting the skin cancer. Coming to requirements to implement, we need basic hardware and software. So coming to hardware, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Coming to software, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap. Now let's execute. To execute, we need to open the code folder of the project, which contains source code files. So these are the source code files in the code folder of the project. Let's understand them. How will they be used in the project? So here in this ISIC folder, we have the dataset used in the project. So these are the 7 different types of skin cancers that are being used to classify the skin cancer. So first, let us open the first cancer type, that is actinic keratosis. Let's open it. So these are the images related to skin cancer type, that is actinic keratosis. Let's get back. Let's get back. And here we have basal cell carcinoma. So these are the images of skin cancer type is basal cell carcinoma. Let's get back. And here we have dermatofibroma. So these are the images related to dermatofibroma. And here in this we have melanoma. So these are the images related to melanoma. And here we have images related to nevus. So these are the images related to skin cancer type nevus. And here we have pigmented benign keratosis. So these are the images related to pigmented benign keratosis. Get back. Here we have vascular lesion images. So these are the images related to vascular lesion skin cancer type. So all these are combined and they are saved as train and validation folder. So in the images which are in the train folder will be used to train the model so that models will be able to classify the skin cancer. And this images which are in the validation folder are used for evaluating how the models have been trained for classifying skin cancer. Let's get back. So coming to the sample folder, here we have the test cases. So images which are in the classification are used in the front end as a test cases to classify the skin cancer, and images which are in the detection are used for detecting the skin cancer in the front end. Let's get back. So this is the static folder. This folder contains files related to CSS, JavaScript, and Bootstrap files, which are important for the visual appeal of the project. The next one is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And here in this YOLO v5, YOLO v8, and YOLO v9 folders, we have the dataset also. So images which are in ISIC are used for training the models for classifying skin cancer, and images which are in the YOLO v5, YOLO v8, and YOLO v9 are used for detection. Let's open YOLO v5. So here there are two subfolders. One is train and valid. Let us open train folder. Here we have two more subfolders, images and labels. Let us open images first. So here they are combined of all the seven types of skin cancers. So these images we will be using to train the model. So train the YOLO model so that the YOLO model will be able to detect where the skin cancer is, and also it will detect which type of skin cancer it is. Let's get back. And coming to labels. So these are the label files or the annotation files for the objects in the corresponding images in the image folder. Here each file represents a each file corresponds to an image file in the image folder, which provides details about object locations and classes within the image. For example, the first label file corresponds to the first image file in the image folder. It corresponds to this and it provides the object locations and classes of this skin cancer. Similarly, for all the 1763 images, we have corresponding 1763 label files, and that too in the order. Each YOLO file, they follow the YOLO format. For example, let us open one file. Here, this line represents a detected object. The first number we have is the object class index, followed by its bounding box coordinates. So these are the bounding box coordinates. This is the X limit, this is the Y limit, this is the width, and this is the height. Zero is one type of skin cancer, and we will also have other other class indexes. Suppose we will be having one that represents another type of skin cancer. Similarly, we will having from 0 to 6, which are seven types of skin cancers. Let's close this. Similarly, we will be having in all the 1763 label files. Let's get back. Train is used to train the model so that YOLO model it will be able to detect, and validation is used to evaluate the trained model. Let's get back. Here in the YOLO V8 and YOLO V9 also we have same images, but they are annotated differently because each YOLO version requires its own specific type of annotations for training and testing the models effectively. Having separate folders helps keeping the dataset organized, ensures that each YOLO version receives the correct annotations it needs function properly. And here we have app.py file. So this .py file contains the information related to front-end logic of the project. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. And here we have model files. Here we have two model files that contain the algorithm information, and that will be loaded into the project code during runtime of the project. And here we have two Jupyter Notebook files, which contain the combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. So in the classification Jupyter Notebook file, here we will be training the models so that they will be doing the classification. And in detection part, we will be training the data so that we will be training all the YOLO models on the data so that they will be able to detect the skin cancer in the image. Now it's time for execution. Let's copy the path of the code folder from the address bar of the file explorer. I've copied the path. Now open the Anaconda prompt. It has been opened. Now give the command cd followed by the space, give the paste path. Paste the copied path. Now click on enter. By this command, current directory will change to the code folders path. Now we need to compile app.py file by giving the command python space app.py and now click on enter. So this command, it will execute the Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address, which will be the local host and the port unless configured differently. It's taking time, just wait for a while. So here we got the link. This is the local host and this is the port. Now copy this local link provided by the Flask framework and paste it in any web browser. I'm copying the link. I prefer Google Chrome, so I will paste it in that. Paste the link here, click on enter. This is the web page of the project, which is displayed in the browser, and this is developed using Flask framework. Now register first, click on register and enter all the registration details if you are registering newly. I have already registered, so I'll directly sign in, click on sign in. Give your username and the password and click on login. We have logged in successfully to the detection and classification of the project. As we're doing both the classification and detection first, let's do the classification. So click on classification. Here you can see choose file button, right? We need to click on that for uploading the images. So we need to click on that. So let's open it. Let's open the sample folder in which we have test cases. As we're doing classification, open classification. Now we will be predicting all the 7 types of skin cancer and check whether the application it will correct predictly or it will correct in a wrong way. So let's open the actinic keratosis and see whether it will predict actinic keratosis or something else. Let's upload this image, click on open and now click on upload and detect. So what will happen is this image will be processed at the backend and then trained model will be giving us a prediction. So this is the image that we have uploaded and here it has predicted as patient is diagnosed with actinic keratosis. So here you can observe that application is correctly predicting the actinic keratosis. Application is nothing but your trained model has been correctly predicted the actinic keratosis. Now let's check with the one more image and see whether it will predict correctly or not. Let's upload this one. So this is the uploaded one and here we have the prediction and here it has correctly predicted that actinic keratosis. Now let's check with one more class. Click on choose file. Now let's try with basal cell carcinoma. Let's upload this image. So this one is the uploaded image and here we got the correct prediction that basal cell carcinoma is being diagnosed to the patient. Let's try with one more disease, one more image of the same disease. Let's upload this one. Click on open and now upload and predict. So this is the uploaded image and here we have the prediction that patient is diagnosed with basal cell carcinoma. So now let's check with the one more test case. We have completed 2 test cases as of now. Let's try with the one more test case that is dermatofibroma. Let's upload this image, click on open and now upload and detect. Here we got the detection, that is classification. So this is the uploaded image and here we have the detection. Here we have the prediction that is patient is diagnosed with dermatofibroma. So here it has been correctly classified. Let's try uploading some more images. Let's upload this image. So this one is the uploaded one. Here we got the correct prediction that dermatofibroma is detected. Now let's check with the other class. Click on choose file. We have completed actinic keratosis, basal cell carcinoma, dermatofibroma. Now let's upload melanoma. Upload this image. Click on upload and detect. So this one is the uploaded one and here we got the prediction that patient is diagnosed with melanoma. So here this is the image that we have uploaded and here it has correctly predicted as melanoma. Now let's try with one more image. So let's upload this one. Here we got the prediction that melanoma is diagnosed to the patient. Let's check with the other class. Click on choose file. Up, open Nevus, open this one and click on upload. So here we got the prediction. This is the uploaded one and here we got the prediction as Nevus. Let us upload one more image. So now let's upload this image. Click on open and now upload it. So this one is the uploaded one and here we got the prediction that Nevus. Let's try uploading some more of the other class. We have only just 2 remaining test cases pending. So let's upload this one. Click on upload and detect. And here this is the uploaded one and here we have the detection that it is diagnosed with dermatofibroma. Let's upload some more. Click on choose file. Let's upload this image. Click on open and now upload it. So here we got the prediction. So here we got the prediction that it is diagnosed with pigmented benign keratosis. So this is the image that we have uploaded and here we got pigmented benign keratosis. Let's upload one more. So now let's upload this one. So here we got the prediction that pigmented benign keratosis is detected. Click on choose file to upload the last case, that is vascular lesion. Let's upload this one. Click on open and now upload it. So here we have uploaded this image and here we got the prediction as vascular lesion diagnosed. Let's try with the one more image. So now let us upload this image. So here we got the correct prediction that vascular lesion classified. So now we can understand that application is correctly classifying the skin cancer. Now let's check with the detection part. Click on detection and see whether it will detect the skin cancer properly or not. Click on choose file. Open the detection folder. So these are the images we will be using as a test cases. So let's upload this image. Click on upload and detect. If you observe here, application has correctly detected the basal cell carcinoma. Here, a bounding box is drawn around the skin cancer, that is basal cell carcinoma, and a class label of basal cell carcinoma is given with the 0.76 probability score. Probability score is nothing but it is how confident it is in detecting this particular class. Let's get back. Click on choose file. Now let us upload some more images. Click on choose file. So now let us upload this image. Click on open and now upload and detect. So here if you observe, place where benign keratosis is present, a bounding box is drawn around it and it has given label as benign keratosis with a 0.51 probability score. Now let's try uploading some more images. Click on choose file. And now let's upload this image. Click on open and now upload it. Click on upload and detect. So here cutaneous fibroma is detected. So the place where cutaneous fibroma is there, a bounding box is drawn around it with the 0.54 probability score. Now let's try uploading some more images. Click on choose file. So now let us upload this image. Click on open and now upload and detect. So here melanocyte nevus of 0.76 probability score is detected. So here is the melanoma nevus and a bounding box is drawn around the skin cancer. It is detecting where that particular skin cancer is. And here it is giving you the class. Let's try uploading one more image. Click on choose file. And now let's upload this one. So here, place where melanoma is present on the skin, it has been detected with the 77% probability score and 31% probability score. Let's get back. Click on choose file. Now let's upload this one. Click on open and now upload and detect. Here, solar keratosis is detected and a bounding box is drawn around the skin cancer. So now I will show you the difference. What is difference between classification and detection? Because from starting itself, you're hearing what is classification detection, right? Now I will show you through the test case. Let's get back. I'll tell you first what is classification and then I'll explain you what is detection. So click on choose file. For example, let's upload this image. Click on open and now click on upload and detect. So here we got the detection, that is prediction as basal cell carcinoma. Here basal cell carcinoma is classified. Here classification is nothing but it is just looking at the picture and detecting what it is. So here by looking at the picture we are just justifying that this is basal cell carcinoma. Now coming to detection part, let us upload the same image. Click on choose file. So this image that we have uploaded, right? Click on that, open it. Now click on choose file. Here, basal cell carcinoma is classified, but here it is detected. So this is a place where that disease is there. So it is detecting and drawing bounding box around it. Here, it will not only just figure out what is that image, but also finds out where it is. So this is the detection between classification and detection. I wanted to show you through pictorially, so that is why I've explained you in the ending. Through this, you will understand it clearly. Get back. Now let's check with the graphs. Click on graph. So here we have graphs for the classification first. So these are the models that are trained for classifying the skin cancer type. And here on x-axis we have accuracy score, and on y-axis we have the algorithm names. And here similarly we have precision, recall, FN score graphs. FN score, precision, recall, and accuracy are the error metrics used to evaluate all the classification models. And coming to the detection part, this is the precision recall curve graph. Here on x-axis we have recall, and on y-axis we have precision. This is the F1 confidence curve graph. Here on x-axis we have confidence, and on y-axis we have FN score. This is the confusion matrix, where on x-axis we have true values and on y-axis we have predicted values. Moving on, this is the precision score, recall score comparison graph, and this is the mean average precision comparison graph. These are the algorithms trained so that all the algorithms, they will be able to detect the skin cancer where the skin cancer is. So mean average precision, and recall are the error metrics used to evaluate the detection models. Now log out. In this way, just by uploading images to the system, if you want classification, we can do classification. That means we will get what is the type of skin cancer. If we want event detection, it will a bounding box will be drawn around the skin cancer, and it will classify which type of skin cancer it is. This will help both the patients and also the doctors to diagnose it in the early stages itself. This is all about the project.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.